So hello everyone, I'm Ayman and I'm going to present ambiguous medical image segmentation using diffusion model. Um, so existing AI research in medical image segmentation focuses on imitating individuals rather than utilizing collective expert insight. So in this paper, we introduce a diffusion model-based approach that generates multiple plausible segmentation masks by learning a distribution over group insights. So the proposed model utilizes diffusion stochastic sampling process to produce diverse segmentation variant with minimal additional learning. The model's effectiveness is demonstrated on CT, ultrasound, and MRI images, outperforming existing state-of-the-art method in accuracy and preserving natural variation. So a new metric is proposed to evaluate both segmentation diversity and accuracy, catering to the interest of clinical practice and collective insight. Um, so in the traditional segmentation model, we have deterministic network that provides fixed mask for each input. This means there is no disagreement about the boundaries of the object. However, in medical cases, different experts may have different opinion about the extent of the anomalies. This is where probabilistic networks comes in, as they allow for flexibility and account for the varying viewpoints of experts. Um, so deterministic network generate a single mask for each input. To introduce probabilistic element, VAE-based network incorporates latent variables sampled from a prior distribution. These variables are injected into the last layer of deterministic network, enabling probabilistic output. However, a limitation arises as this network rely on the specific prior distribution chosen. Um, Lastly, probabilistic network also requires an evaluation metric similar to deterministic networks. The widely used metric in this context is generalized energy distance. However, the GD metric has a drawback in that it tends to excessively reward sample diversity without adequately considering how well the prediction match the ground truth samples. So, in summary, our contribution is an innovative diffusion model-based approach for ambiguous medical image segmentation. Our method generates diverse segmentation masks by learning distribution over group insights. It outperforms existing method in accuracy and preservation of natural variation. We also propose a new metric to evaluate both segmentation, diversity, and accuracy, catering to the clinical practice and collective insights. So, regarding our method, at each diffusion step, we utilize two axial aligned Gaussian encoders. So the first encoder, which we refer to as ambiguity modeling network, encodes the input image and the ground truth mask distribution. The second encoder, known as ambiguity controlling network, that encodes the input image and the predicted mask distribution. To train our model, we minimize the KL divergence between these two distributions and incorporate the loss into the diffusion model. During the inference stage, we introduce different noise variation with each input image, resulting in a distribution of prediction. So this approach allows us to capture the ambiguity and generate diverse segmentation output. We propose a new evaluation metric called CI score, collective insight score. It addresses the limitation of GT metric and includes three components: combined sensitivity, maximum dice matching, and diversity agreement. These components, inspired by clinical practices, provide a comprehensive assessment of the segmentation performance. So in CI score, we have combined sensitivity that measures the true positive rate by considering both prediction and ground truth distribution, um, aligning with the clinical practice objectives. Then we have maximum dice matching that calculates the maximum dice score between individual prediction and all ground truths, enabling comparison of student diagnosis with expert opinion. And then we have diversity agreement that assesses the diversity of predicted output by comparing the variance between ground truth and prediction distribution. The CI score is defined as harmonic mean of the combined sensitivity, maximum dice matching, and diversity agreement components, providing a comprehensive measure of segmentation performance. So our approach demonstrates strong performance across all three modalities, that's CT, ultrasound, and MRI. Quantitative result shows the effectiveness of our method in achieving accurate and reliable segmentation outcome. Um, since evaluating ambiguous networks possesses challenges in terms of characterization, we argue that qualitative results can serve as a valuable indicator of network performance, particularly in complex cases. Our method showcases visually superior and diverse outcomes, for further supporting the effectiveness of our approach in addressing ambiguity and producing high quality segmentations. Um, So furthermore, our proposed method CIMD demonstrates improved performance in avoiding partial segmentation. It effectively addresses the issue of incomplete or fragmented segmentation, resulting in more accurate and comprehensive delineation of desired objects in the medical images. Um, Thank you.